Hey everyone, welcome back. In this short video we're gonna look at how to work with a Wii Nunchuck controller from within an embedded system program, which in my case runs on a Nucleo L053R8 board. However, the source code that works and polls the Nunchuck controller for the purpose of reading all the buttons and joystick and the accelerometer data can be used separately as standalone code with any other project, Arduino or whatever have you. And in this case, this is an example in a lab in one of my courses in which I'm reading and polling repeatedly the Nunchuck. I'm reading the data and display it right here on a tiny LCD display. Where I display the joystick X, joystick Y, as well as the accelerometer data X, Y, Z, and the status of the two buttons Z and C. At the same time, the joystick data is used to control the movement of a little circle drawn on the LCD display as well. So let's go and create a new STM project. All right, let's create a new project, new STM32 project, and then go and select board selector and navigate to find our board, which is a Nucleo L03 L053R8. Click next. Let's name it lab 7 example 2 underscore CPP, because this is going to be the CPP version of our previous example 1 that was in C. Select as targeted language C++. Leave everything else as it is and on default settings, and click finish. Initialize everything with the default settings. Wait a second or two for this to be created, and then we get directly into the CubeMX, the graphical tool that allows us to select and configure different peripherals for our project. The first one that we'll be adding is, like we did in the previous lab, the SPI1, which we would like to enable and use pretty much most of the default configurations, except that I will select a prescaler 4 high here, and then that's pretty much it. The other thing related to this communication with the LCD display is that would want to use GPIOs specifically to chip select, to reset and to data or control the little display that we use. So for that we come here to system core GPIO and go and find those pins. So I need PB6, where are you? PB6, I'm gonna set it as an output, of course. I'm gonna search for PC7. I'm gonna use it as an output again, and I'm gonna look for PA8 also as an output, and we're gonna go and give some custom names for that. PA8 we're gonna use as the LCD underscore data control. The PB6 pin we're gonna use as LCD underscore chip select, and then PC7 we're gonna use it to connect to the reset of the LCD, so we call it LCD underscore reset. So in addition to those two pins PA5 and PC13 that were connected to the green LED and as well as the blue push button, we added PA8, PB6 and PC7, which will be needing to be using together with the SPI peripheral to talk to the and control to the LCD display. All right, so that's what we've done so far. In addition, we will be using I2C1 peripheral to talk to the Nunchuck. We'll be doing some configurations of this guy as well. In case you forget how to do that, you can always come back to the lab description, which will show here in this figure that we would like to use the fast mode and the frequency 400. And let's do that. Fast mode, and I think that's what I asked in the lab to do pretty much it. One other thing that I wanted to do was to use as SCL and SDA, actually not the default pins but PB8 and PB9. So if I go and select from here PB9, then I would like to use it as I2C1 SDA, and then PB8 as I2C1 SCL. That should show up here in the GPIO settings of this peripheral as well now as being PB8 and PB9. The ones that we like to use for I2C1 SCL and SDA. One more thing that we want to do here in the CubeMX is the clock configuration, which I would like to go and use the high-speed internal clock. The other clock configurations will be left as they are. I see here that I2C will be using P-clock1. Yeah, that's pretty much it here. With that, let's save this and close it. The next step is that we'd like to go and do the code generation, so that we'll have the initial main.c and everything else created. And if we go to core sources and open main.c, we'll see that we have created this template file with all the global variables that will allow us to handle and work with the I2C SPI and the default UART already in there. What we need to do now is to actually close this and go and rename it as .cpp and copy over to this project directory a couple of things. The first thing that we'll do, copy, will be to go and take the LCD and UGUI files from the archive that I provided to you and place that into this project directory, drivers, paste that there. The other thing that we will be copying from the given files are the nunchuck. Let's put it there, but we'll put that into core sources. As I said, we'll rename this as CPP because we're targeting CPP as a language, and that's fine. And then we'll be bringing in there the nunchuck that h, put it here. We go back to our project. If you open the main.cpp, is still the template as it was created upon the creation of this project. The next step that we have to do is to bring in here the source code that I have provided in the main.c pp that was included with the source files provided for this lab. So go and open that with a normal text editor and bring with copy and paste the things that that you don't have in the fresh new main.cpp that are related to the implementation functionality of this project. So I'm gonna go and do that step by step. Here. All right, I have copied with copy and paste pretty much everything that implements this project from the given main.cpp into my main.cpp in my new project here. One thing also that we need to do is go into main.h inside the include of your project directory and add these two includes to include the LCD and the GUI into our project. And before compiling, we need to do one more thing, and that is go to project properties and go inside C++ build settings and add to include paths into the G++ and GCC compiler paths to our LCD and GUI folders that we have added to be able to deal with the LCD display. So click on this add here, file system, and select from within your project, in my case lab 7 example 2 CPP, from drivers, first the LCD, okay, and then add also the UGUI, and do the same for the GCC. And that apply and close this time would be ready to compile this project. So let's build the project. All done. All right, we're ready to program our board and verify the operation. So let's go run configurations, double click on that so that we'd create a configuration for this project as well. It's right here, and just run it, and then once the board is programmed, let's go and check how that goes. So let's see. You can see that it was initialized, and you can see already that as I move the nunchuck, the accelerometer, X, Y, Z values are changing. If I press the Z button, if I press the C button, you can see that they are updated over there. If I move the joystick, I can move the little circle as intended. So it's working fine. One last thing I wanted to go over quickly is to briefly talk about the the source code that implements this nunchuck communication and functionality. Coming back here to the main program, you'll see here I have a couple of variables that I will use to store data that I will read from the nunchuck, the joystick X and Y values, the accelerometer values X, Y, Z, and the buttons Z and C. But I really going to use information only about the joystick X and Y to detect whether the user wants to move that little circle to the left or to the right or in any direction. The other values of the accelerometer, the Z and C button states, I'm only using for printing their values onto the LCD. That is pretty much it. Now, if you go and look at the lab document that I have made available and read details about how exactly the communication of the nunchuck goes about, it is essentially boils down to two so-called phases. The first one is to initialize the nunchuck, and that requires us to send this bytes as shown in this figure, and then the second phase we first need to send 0 0, and after that we need to read 6 bytes from the nunchuck every time when we want to read the data from the nunchuck. Those 6 bytes essentially represent all the data that we need: joystick X and Y, the first 2 bytes, and then the next 3 bytes the accelerometer X, Y, Z data. But this data is represented on 10 bits each. These 3 bytes represent the most significant 8 bits of those 10, with the least significant 2 bits for each of those X, Y, Z being packed in the last 6th byte, which also include as the least significant 2 bits C and Z button states. So if you come here back to the main program, you'll see that I create a variable, an instance, an object of that class nunchuck that I have defined right here, nunchuck.h. I'm not going to go over each and every one of this. It's very easy to figure out what is what. It's self-explanatory, everything. But you'll see the phase in it. If you go to it and see it in the nunchuck.cpp, implementing really those 2 transactions to that require us to send F0 and 55 right here, and then FB00 as you can see here. Reading will always send that 00, only one byte, and after that be reading 6 bytes from the nunchuck, which is very simple and very easy. That's basically the communication with the nunchuck. Once I read it here, we need to translate it. The translation is essentially boiling down to taking this 6 bytes and doing the bit shifting and concatenation so that we construct the 10-bit representation of the accelerometer data X, Y, Z, as well as extracting the button states Z and C. All that data will be, as I said earlier, be used inside the main that C forever infinite loop to detect the direction in which the joystick was moved in the X and Y, and then figure out what exactly we need to redraw the circle and erase it first from the previous location to mimic and achieve in this way the movement onto the LCD display of the circle, as you can see over here. So, as I said at the beginning, this C++ implementation is as a standalone implementation could be taken from this project and used and integrated with any other project, with any other microcontroller program that you may want to use. I hope that is going to be useful and helpful to some of you, and thanks for your time.